I'm very happy to talk to this community today about, as you assumed rightly so, a problem Maxime and I came up to discuss and work on when we were in Munich, actually specifically in the same office. So it was quite easy to discuss some things. And this problem of shear-induced chaos has been discussed quite intensely by Lysing Young from NYU and some co-workers starting in mid of the 2000s. And then, during my PhD time, I got more and more into these problems of random bifurcation theory, and in particular chaotic motions and chaotic induction from noise and other parameters. And during my PhD time, I tried to prove something which I just managed to do in a slightly reduced and easier way. And I had thought about using the computer to prove that, but I was not in the right environment and personally not educated in this field enough to do it. And then I met Maxime. So let's explain you how this all went on. I want to give you a little bit of an introduction into these problems of bifurcations in random dynamical systems, but really immediately go to our problem of the Hopf bifurcation with noise. And then introduce you to a concept that I developed together with Jeroen Lamb and Martin Rasmussen at Imperial College, which we called quasi-ergodic random dynamics, and which helps us then to apply a computer-assisted proof technique actually to this problem of stochastic Hopf bifurcation. So let me start with what our basic question has been and sometimes still is. So we look at a stochastic differential equation where the drift depends on some parameter which works as a bifurcation parameter if there's no noise. So if we don't have this noisy term here, which I've written in a Stratonovich way, because we will look at differentiable objects, and Stratonovich integration doesn't change anything in terms of chain rule, and is very easy for differentiation. But of course, we could also look at it in ether noise. So when there's this noise is not coming in, our problems often have some bifurcation in them. So there's some topological change of behavior at a critical value of this parameter alpha, or even more values. And the question is, what does the noise do to this bifurcation? So more specifically, is the bifurcation still present in the stochastic case? And if yes, in what sense? So how could we measure that? And additionally, and this will be more the focus of what we are going to look at, could there even be a new kind of bifurcation scenario in interaction with other parameters that are in the system and that were already there in the deterministic case, but didn't really add anything to the picture? So what I mean by that, I show you in a second. First, I want to give you an idea what kind of objects we usually use here for understanding these problems of bifurcations in stochastic differential equations. So first, a crucial object is to find a stationary or ergodic density for our system, which solves the stationary Fokker-Planck equation. So in the following, this L star will always be our Fokker-Planck operator, which is the formal L2 adjoint of the generator for our SDE, so the generator of the semigroup for our stochastic differential equation. And the generator itself is this second order differential operator, and L star is the, as I said, formal L2 adjoint, and we will see for our particular example how this will look like. So if we are just on the whole space, then we are interested in the stationary solution of this problem. If it's unique, then it's even ergodic, which means that the typical behavior of trajectories will statistically very well be described by this density. So this really shows us how the time averages of our trajectories are distributed in space. And this is more what we would call a statistical point of view on such a problem, and then maybe also see how this density changes in terms of this bifurcation parameter alpha. How we sometimes say a dynamical point of view, or the random dynamical systems point of view, to look at the SDE is actually to look at it in a omega dependent, so for each sample dependent flow-like way. So we have this kind of flow property here if you just look at the usual ODE, then this would of course also just for a fixed omega be the same kind of property, but now with some non-autonomous aspect. So we consider time shifts on our probability space due to the fact that the impact of the noise has a non-autonomous character. So whenever I go forward in time, let's say by a time s, I have to take into account that in this time, I've also gone forward in time on my omega space, or with respect to my path coming from the noise space. So that's why we have this so-called co-cycle property for this stochastic flow. And this RDS or co-cycle property is what we usually get for well-behaved stochastic differential equations. And then we want to look at it given different initial conditions and the same impact of the noise. So I show you now how this looks like for the system we will look at. So this is a normal form for Hopf bifurcation, where the bifurcation parameter is this alpha. So for alpha negative, we will see in a second, there's convergence to the equilibrium at the origin. And then for alpha bigger 0, there is the forming, or at alpha equals 0, there's the forming of a limit cycle, which then becomes the stable object. Or to be precise, this is a supercritical Hopf bifurcation. There would be also a subcritical, but we're focusing on this case here. And then we have some rotation in the beta. This A is not really important here. Important is that you can include this kind of parameter B, which can also be seen as a shear, so as a phase amplitude coupling. And this doesn't affect the dynamics at all if we look at it in this normal form. If there's no noise perturbations or any kind of other perturbation, but if there's some really very simple additive noise here, so just some white noise with a certain intensity sigma, so with a certain standard deviation, which we can scale, then system. For the non-noisy system, then we have convergence to this attracting equilibrium for alpha smaller than 0, and for alpha bigger 0, we have this limit cycle, which is then the attracting object, where the equilibrium has become unstable. And actually, if we only look at the stationary density now, so if we solve the stationary Fokker-Planck equation, then we find a unique solution and will actually be able in this very easy case just to compute it explicitly. And we see that there's no dependence on the shear parameter B, but it's actually really mirroring the bifurcation quite nicely. So you have for alpha smaller than 0 that there's this one peak density, and for alpha bigger than 0 you have this crater-like density, where these maxima really correspond with the attracting objects in the deterministic case. So nothing really interesting happens there, but now if you look at it a little bit differently, namely from this random dynamical systems point of view, then something happens. So we introduce something we call random attractor, which is like an attractor in the deterministic sense, but now depending on this omega, because in the random dynamical system setting, we always look at these fixed samples or these fixed probability samples out of our probability space. And for that, we want to define this, this object, or to find such an object as a random attractor, which attracts the flow. And we write it very often in a pullback sense. So we go back in time on our omega space and go forward in time exactly the same amount in order to fix the object at the omega. Otherwise, we would have to shift with the theta t again in forward in time. And very often these notions are equivalent, but by that we can look at a fixed object omega. So I show you a picture. So this is just starting with different initial conditions and then applying the same noise realization to all these different initial conditions. And we see here that if there is small shear, but already actually positive alpha, then the noise actually leads to a so-called synchronization. So we have all these points which are forced by the same noise. In this pullback sense, we're always going back in time on the omega space and then forward in time exactly this amount, will actually just be contracted to this one point. In the other case, when the shear is very large, we see some new behavior, and this is actually this kind of chaotic random attractor. So we still have contraction overall, so there's volume contraction, but then in the leading behavior in this contracted area, we have some divergent behavior and we get this fractal-like object. And I just want to show you for a second, maybe a short video to illustrate this a little bit more even. So let me just show you this video. So you see here that, yeah, maybe we start again. It just starts again in a second. So we start with this big point cloud, and now we apply the same noise. And then actually it's attracted to this one area where there's a random attractor, but then on this area of the random attractor, we still have some divergent dynamics going on. And this kind of, yeah, chaotic random motion on a random attractor, of course, is a very interesting effect, and it really comes from this interplay of the noise and shear. So if we go back to our slides, sorry, why is this here? Should be, yeah. If we go back to our slides, then yeah, we can see that there's this attraction to this random attractor, and now we want to measure when does that happen. I will explain later, maybe a little bit more again when we come to the particular model, which will also help the computer-assisted proof.
Sorry, I have a question.
Yeah.
So this row in the, let's say this bottom row is for alpha minus 1. So in deterministic case, it's just attracting 0, right?
Exactly. So what I want to show here is that that's what I wanted to mention. So if the alpha is positive, then this B would not be needed to be so big to get this quadratic random attractor. But the story here is why I chose these parameter connections is that here you see that the alpha really doesn't matter for the bifurcation anymore. So the bifurcation in the random sense now is really from a synchronization or from a random point attractor to this random chaotic attractor. And it doesn't depend on the alpha.
Sorry, so in this upper row, so your attractor is at the end, what? Point or periodic orbit? Ah, so this is, okay, this is, so that point in the right top diagram, right? Is in fact some kind of periodic thing, or not periodic, I mean moving thing, right? Or not?
Yeah, exactly. If you look at it in this pullback way, then it's a fixed thing. But if you now go forward in time, then it would be a moving. So that would be an attracting synchronization solution. Exactly.
Okay.
Yeah.
Okay.
Precisely. And the idea is that when this alpha is positive, so if this alpha would be negative, you would have exactly the same. So I chose this to show this double effect. So actually, if there's small shear, then whatever noise, whatever alpha and noise, we will see the synchronization, even for positive alpha. If there's very large shear, then even for negative alpha, but in particular for positive alpha, and this is what we will actually choose a positive alpha for the proof, because this is easier. You don't need the super large shear, but this already shows this kind of there to show you that the shear force really becomes the new bifurcation parameter for the random case, and this alpha doesn't really actually matter in that sense anymore. So the point is now how to prove such a thing, how to prove this existence of or at least, or to prove that there is this chaotic random attractor. Existence of these attracting objects is not so hard to show for such an explicit example. But we want to actually measure the dimension of the attractor or the nature of this attractor. And classical way to do that is to look at the Lyapunov exponents. So in particular, the first Lyapunov exponent, which is the largest Lyapunov exponent, which gives you an exponential rate of expansion or contraction along your trajectories. So this is actually measured by looking at the Jacobian of your random flow. So you look at derivatives with respect to space, so with respect to your starting point, and then along the flow, and then you look at how this expands or contracts on the tangent space. So you take vectors of the tangent space, you look at the Jacobian along the flow, and you measure now with which rate, in an asymptotic way, in different directions of these tangents, of this tangent space, the system linearly contracts or expands. Apart from a zero measure set, actually, you will usually observe the first Lyapunov exponent when you take any of these vectors. But of course, we have this kind of still generally attracting setup. So volume is contracted, so the sum of these Lyapunov exponents is negative, but the first one might be negative or positive. And what we can prove for the system I showed you, what we proved 2 years ago or 3 years ago, was that if the shear is small, then as I said, there's actually synchronization or contraction to a random point or random equilibrium, because we have this negative Lyapunov exponent, and you can then really show that it must be a random equilibrium because we have uniform contraction in all directions. The point is now it's very difficult to show the other case. So there is a certain formula for the leading Lyapunov exponent, and this comes from actually just really directly computing your linearized object. So if I just briefly go back to this dx phi, so if you look at this object and you look at it in polar coordinates, then you're basically only interested in what the radius does. And what this radius does, this is just in a linear equation, depends on what your original system does, so what happens along, or what happens in your original nonlinear system in a linearized way, so in terms of the Jacobian along your vector field, which comes from the SDE. If there would be not just additive noise, this would be a little bit more complicated, but here it's really just enough to look at the drift Jacobian, and then in a certain functional with the directions on the tangent space. So this S comes really from the directions on the tangent space. So the process you look at is a process on the unit tangent bundle. So you look at it on the original and on the tangent space. And then you want to find a joint distribution for this unit tangent bundle. And if everything is nice and ergodic, then you can write it as this closed integral formula. So this S part here really comes from the linearized or from the tangent problem, and this R2 part comes from the original problem, and you get this kind of formula, also called Fürstenberg-Kosminski formula. And now you can maybe imagine that it's much harder to show that this is positive here at for some parameter values than to show that it's negative, because in a negative case you might, and this is actually the case, sometimes just have that this object is negative, or you can find some upper bound, right? And if you have an upper bound for this functional here, then you don't even need to know anything about this distribution, then it's definitely negative. But if you have negative and positive directions of this functional, which just means in a chaotic random attractor, you will always have that, because you have definitely contractions, otherwise you wouldn't have an attractor, but you also, of course, have then in the chaotic case some positive directions. So it's very hard to make actually an estimate on that, because you really need a lot of information about this three-dimensional distribution. So this is very hard to show that this lambda 1 can be positive for certain of these parameters and to show the chaotic random attractor. But what we could do was to prove for a slightly reduced linear model, as also in a similar way conjectured by Lyapunov, that there is a positive Lyapunov exponent. But this is really not the same model as what I showed you, but a slightly easier one. So the question is, how can we prove this positive Lyapunov exponent for the full model with this large shear force, so with this large stretching folding via the amplitude phase coupling? And how can we control higher order terms if they come also into play? So this is a little bit more of a general question. If we have these bifurcation normal forms, but we might have some other nonlinearities, then how can we deal with them, since we're actually interested in these local movements, but we have this noise which makes everything global. And one idea to deal with this was to look at so-called kill processes and replace some ideas of stationarity and ergodicity by quasi-stationarity and quasi-ergodicity. So as I said, so you can observe that the stability and bifurcation phenomena are local, but the noise is global. Yeah, apart from making things easier to compute, it's also a philosophical aspect that you would say, if you have random bifurcations and you don't want to be shifted around all over space, but really focus on some areas, then it might be better to come up with a kind of different setup. And the setup we chose was to consider such a process which solves the stochastic differential equation on a bounded domain, and really looking at this process until it touches the boundary of this domain. So this will happen with a certain stopping time, and then just say that whenever it has hit this domain or this boundary of the domain, we will forget about it. It goes to some cemetery state, and we recondition the whole dynamics. So we just really always look at the surviving trajectories within this domain. And people from stochastic analysis have done quite a lot about that. So one first thing is that you would replace stationarity by so-called quasi-stationarity. So since you lose mass out of this bounded domain, you can't really have stationarity, but you can have quasi-stationary distributions, in the sense that if you start with a probability measure and now you check where your trajectories are, for example, if you want to see the probability with which they are in some set B, then what you look at is not really this pure probability, but a reconditioned probability on surviving in the set. So you really take the probability of your process xt being in the set as a proportion to all the trajectories that have survived up to this point. And really only conditioning on the survival, you check if this probability actually, when you start with the quasi-stationary distribution, is then still exactly this quasi-stationary distribution. So it's this changed form of stationarity with reconditioning. And the question is now, can we use this also, as we used some ideas of stationarity and ergodicity to compute Lyapunov exponents in the original case? Can we also do this now for the this kind of killed setup? And what we do is we observe that if we have such a additive noise stochastic differential equation, as we saw it before with this example, and our drift is differentiable, then first maybe we just look at the finite time Lyapunov exponents. So we look at these rates of contraction and expansion up to a certain time, which is always smaller than our killing time at the boundary for a given starting point and a given noise realization. And again, this dx solves our linear variational equation coming from the problem. And actually, we get this kind of formula. So now I wrote it down in a slightly more complicated way. But this is exactly what you saw before. This is this functional from before. And usually with ergodicity, we would see that these time averages, they converge to some integral with respect to an ergodic distribution. But in this case, of course, first of all, we are only looking at the finite time problem and then want to see what kind of convergence can we get. And here again, this ST is just the direction, or just the unit tangent bundle part of the linearized process. So the idea would now be that this quasi-stationary measure is maybe the right limiting measure for getting a closed formula for these objects. And we know actually from some work before that the uniformly elliptic STEs have quasi-stationary distributions, and actually such that the expectation of any observable with respect to our stochastic flow, or if we write it in the process sense with respect to our process, again, conditioning on survival, that they will converge to these observables being measured with respect to a quasi-stationary distribution. But you see that this is not about time averages in this formula, but this is really only if I always take observables of the process at a particular time where we have still survived. When I now take time averages, I will take realizations of this process before this time actually. So I need to take this into account, and then actually the quasi-stationarity is not the same as something that we know from ergodicity, where the time averages actually become the same. So we need to correct this. And I'm telling you this because this will really come up also in the proof done by Maxime. So we need to find some other notion of ergodicity here and some ergodic limit for the time averages. And this exists, so this was already done in the 90s, that you have this, what I would call quasi-ergodic distribution, where actually you look at the time averages of these observables with respect to the process, and you have in conditioned expectation some convergence to this closed integral with respect to your quasi-ergodic distribution. And the point is that this QED, this quasi-ergodic distribution, is not necessarily the same, or generally not the same as the quasi-stationary distribution, but it is absolutely continuous with respect to this quasi-stationary distribution with some density, call it eta here. We don't have to go into details how this exactly works, but I just want to show you that you really can find this quasi-ergodic distribution as a product of this quasi-stationary distribution and some other function eta, and they are both eigenfunction of the Kolmogorov operators. So the nu really is an eigenfunction of our L star. So it's kind of the analog to the classical stationary distribution. And the eta is an eigenfunction of our generator, where it has this property that it's really measured by survival probabilities starting at certain x's, starting at certain points x, then in the product with our survival probability with respect to the quasi-stationary distribution. And this also has a particular rate, the survival probability with respect to the quasi-stationary distribution, and it's actually this lambda 0. And this is precisely the eigenvalue with which corresponds with these eigenfunctions. So let me then just explain briefly that if we have all this, so this quasi-ergodic distribution, which, under good elliptic conditions we will find, so if we have this quasi-ergodic distribution for the unit tangent bundle process, so for the original plus the directions on our tangent space, then we can define something we call the conditioned Lyapunov exponent, which is now really this expectation of these finite time Lyapunov exponents always conditioned upon survival. And in the limit, we get this formula as before. So we get a Fürstenberger-Minsky formula, a functional with respect to this quasi-ergodic distribution. But really note that this is a joint quasi-ergodic distribution, so this is not very easy. You really need to take into account the process, the original process, and the one on the tangent space. And just a few remarks. So these finite time Lyapunov exponents here, these lambda v, they converge to this conditioned Lyapunov exponent in LP for p bigger equal than 1 and smaller equal than 2, and by that also in probability. So there's a lot of physical meaning to that. This is not just some expectation, but really, a strong form of convergence in the setup. For this negative conditioned Lyapunov exponent, you can actually prove some local synchronization again. And if it's positive, we see it as a measure of chaos. And of course, if you let your boundaries of the now bounded domain with this killing at the boundary, if you let that go to the whole space, then you will actually approach your original Lyapunov exponent exactly by this conditioned Lyapunov exponent. Okay, so let me now bring you to the problem again and how Maxime will tackle it, or start, at least give you the setting for what he will apply computer-assisted proofs to. So we come to this problem I showed you with these pictures, with the chaotic random attractor in certain cases of shear. And now look at it in a transformation to polar coordinates. So you have here a radial direction, which is quite well behaved apart from the small singularity here at R, which you get by Ito transformations. And then in the angular variable, you really see how the shear comes in here, namely exactly by phase amplitude coupling. So when the amplitude or the radius is quite high, then you get quite a lot of perturbation in the angle, and this is exactly what leads to stretch fault mechanisms. And why we would expect chaos actually for something like that. But we need to prove it. And what we can do now to make this problem of the unit tangent bundle problem a little bit easier, so we introduce a certain angle which is a combination of actually, again, our ST, so coming from the unit tangent bundle process, and our phi t, which is exactly this angular direction from the polar coordinates. And this lets us write the whole problem now. So the whole problem for the Fürstenberg-Kosminski functional, which would actually be a three-dimensional problem in a two-dimensional problem. So we can, this goes back to DeVille and et al. I mentioned this paper at the beginning, where they found this a little bit easier way of writing the problem here. And really what you need to know for the next half is that, that this is now a, so we have this Fürstenberg-Kosminski functional, we have this problem of the Lyapunov exponent, but now we can actually look at the whole problem with respect to this two-dimensional system of the radial component coming from the original process here, and the psi component combining some part of the original with the linear process. And then you get this this two-dimensional SDE system. And in these coordinates, the functional reads like that, such that, I say something about this in a second, but such that the formula for the largest Lyapunov exponent is now like this in the original setup. So you have this functional E of R psi, this one. This depends on these two variables. And you can express a Lyapunov exponent by E of R psi with respect to a stationary density in the original problem, where the stationary density solves the stationary problem with respect to the Fokker-Planck operator or forward Kolmogorov operator. And these operators, they look like that. So this again was the generator or backward Kolmogorov operator. This is the forward Kolmogorov operator. And Maxime will talk about this in more detail. I just want to mention here, these are second order differential operators. And what doesn't make it so easy is that you have in the Laplacian part here, you have a non-constant Laplacian, but you have these dependencies in the psi direction on the R. And this made our life a little bit difficult at the beginning. In particular, what we didn't really do, and this is my last step, is why did I tell you all the stuff about quasi-ergodic dynamics and so on, is that we didn't really tackle now this particular problem here for the whole space, because this is really extremely difficult on the whole space. And we really wanted to use this new machinery of the quasi-ergodic dynamics on a bounded domain, where we also can say something meaningful about a Lyapunov exponent, namely this conditioned Lyapunov exponent. And we really wanted to use this for a slightly easier way of doing a computer-assisted proof. So we go into a domain where we look at an annulus actually, away from zero. And our conditioned Lyapunov exponent is now exactly this expression with respect to this quasi-ergodic distribution, which again is a product of these two eigenfunctions E and eta and phi with respect to the largest eigenvalue lambda 0. So we have these two eigenfunctions, eta for the generator, phi for the Fokker-Planck operator, with absorbing boundary conditions on our domain. And on the boundary of our domain. And we will use this kind of setup now to compute this conditioned Lyapunov exponent and actually try to prove this conjecture from the beginning that for certain parameter values of the shear, we would see and actually, rigorously then see the positive Lyapunov exponent. Okay, so just a short summary. We saw this highly challenging problem of proving a positive Lyapunov exponent in this stochastic Hopf bifurcation problem. We introduced this conditioned Lyapunov exponent as a kind of new relevant concept for stochastic bifurcation theory for several reasons. In particular here, it will help us actually to give a suitable setting for a computer-assisted proof of the shear-induced chaos. So with this I would hand to Maxime.
Okay, so thank you, Maxi. So I don't know, maybe if there are already questions, you could ask them now or keep them for the end of the talk as you wish.
Just one thing to keep to try to understand. So essentially, when you speak about conditioned, it's like taking your Fokker-Planck and setting zero boundary condition.
Yes.
Okay, perfect.
Yes, exactly. So I was a little bit quick about that, but that's precisely the point. We really assume that the trajectories are absorbed at the boundary, which means then for the operator, if you look only at the nonlinear process, this would give you exactly the Résumé boundary conditions or absorbing boundary conditions at the at the boundary for your operator as well. It's a little bit different here because we also have this angle, as I said, from the linearized problem. So this will give you some periodic boundary conditions in addition, but you will see this in a second.
So let me directly start where Maxi left us. So the goal is to compute rigorously this Lyapunov exponent via this formula and eventually get a proof that it's positive for well-chosen parameters. And so for that, we need to rigorously compute eigenvectors of this Fokker-Planck operator L and L star. And also we not only need to compute rigorously any eigenvector, but to check that we have the correct one, the one which corresponds to this quasi-stationary density and everything. So those are the two steps. I'm actually going to focus mainly on the first one. The second one is actually, in this case, turns out to be quite easy. I will tell you in the end how we do it. Okay, so again, just to remind you, those are the operators. So as Maxi said, reasonably well-behaved operator in the sense that elliptic, uniformly elliptic on a bounded domain. So the spectrum of those in particular is going to be reasonable. We will use that in the following. And okay, the first order terms, of course, we have explicit formulas for them, but they play a role in the numerics, but not so much in the theoretical analysis. So those are the formula that you don't really need to care about. Okay, so the main question is how to rigorously compute an eigenpair for, let's say, L. I mean, as you can see, L and L star, they are quite similar structure. So I will explain it for one of them, and then for the other, you can trust me that it works the same. And so for this, we're going to use, at least on a general level, a strategy which is very standard in this computer-assisted proof community, which has been presented many times in this seminar already. So I'm going to be a bit quick about that. But of course, if there are people in the audience which are not so much familiar with that, please interrupt me if you want. So the starting point for this is to get a numerically compute. We'll give you some details about how we do the numerics in the end, but at this level, it's not so important. One way or another, you numerically compute an approximate eigenpair, so the eigenvector u and the eigenvalue lambda. And then you turn this into a zero finding problem. So I'm going to rewrite my eigenvalue problem as an f equals 0 problem on some space. So of course, there is some choice to be made about the spaces. Here I already made them for a reason that you will see later, but at this level, you could choose different spaces. And maybe just one quick remark is that to the eigenvalue problem, I had this normalization condition so that in order to isolate the solution, so that I don't have a one parameter family of solutions, really locally isolated solution, or in order to make the problem non-degenerate, if you wish. And so now we have this f equals 0 problem for which we have an approximate 0, and the goal is to prove that near this approximate 0, there is a true solution to that problem, and to get small and explicit error bounds. So to do that, we introduced a Newton-like operator, which is written like this. So the only difference with the true Newton operator is that we fix derivative here at the numerical solution and not at u and lambda. And so of course this operator, its fixed points are in one-to-one correspondence with the 0 of f. So proving the existence of the 0 of f is the same as proving that this has a fixed point. And so to do that, we are going to show that on a small neighborhood and small explicit, actually on a ball, on the given radius which we control, close to the numerical solution, this is a contraction. And then by the contraction theorem or Banach's fixed point theorem, call it however you like, we'll get the existence. So again, this is quite standard, as I said, in this community. And in order to prove the contraction, we have a main tool, which we always use. Sometimes we write it a bit differently, but it's some kind of Newton control-rich theorem, which works as follows. So you need 3 estimates. So the first one is this, with this constant epsilon, which control the residual error. Then you need to control the derivative, or more precisely, the inverse of your Jacobian at the numerical solution. And then you need some kind of Lipschitz control on the Jacobian. So in our case, since the problem is quadratic, the Jacobian is just linear, and I can get this globally. If the problem was a bit more of higher order, I might only look at this on in a neighborhood of the numerical solution that would be enough. And so this theorem, it gives me an explicit condition, which is written here. And if that is satisfied, then I can prove that my Newton-like operator is contracting, is mapping the ball into itself, and so I have a fixed point. And I have an explicit error bound with size r, which is a formula which you can compute in terms of those quantities. So this theorem in itself is not so difficult. What is really difficult here is that you need those constants. You do not only need to prove that there exists an epsilon, a kappa, and a gamma, but you need to have them explicitly, because then you want to check if this inequality is satisfied or not. And so again, those of you who use this kind of techniques, you know that, okay, maybe not all the time, but most of the time, the crucial part, the one for which you have to work the hardest, is the kappa here. Epsilon is usually not so difficult, although maybe you have to work a little bit to get it very small. Gamma is fine. And so what I'm going to focus on is this kappa here, or to get this kappa. Okay, so as I said, this is the most challenging part. So just to remind you, this is the operator L, this is the F. And so this is the thing we need to control. Or if you want to write it a bit differently, because of course, a priori, we don't even know that this is invertible. So this is maybe a nicer way of writing it, but it's the same. And so as far as I know, there are mainly two different strategies to get such an estimate. So one of them, which is used by most people actually, I think, in this community, is to introduce an approximate inverse of your Jacobian, which is which you will build using the numerics, and which would be easier in the sense that you can easily compute or upper bound its norm. And then if you do that, and you can also prove that this approximate inverse is quite good, in the sense that this estimate with the delta less than 1 is satisfied, then you get that the Jacobian is invertible, and you get an upper bound of the Jacobian, which depends on just this delta and the norm of it. So that's actually the strategy I'm the more familiar with. But for this problem, I mean, those of you who know a little bit will already immediately see, I think, that this non-constant coefficient here in the second order term makes our life a bit easy, a bit hard here. So I wouldn't know exactly how to apply the strategy here, except maybe if you, let's say, use the structure a little bit more and really go back to the thing that this is some kind of Laplacian or written in polar coordinates. And then you could maybe think about using the Zernike polynomials, as Ariel Koch did recently on a problem which in some sense is a bit similar, at least from the structure. But okay, this, we didn't try that. I'm not even sure I know about this when I knew about this when we started this project. So we did something different. And so what we use is the second option, which is to really work in Hilbert spaces and then use the structure to get this kappa via eigenvalue bounds. So this is what I'm going to explain now. So just to give you maybe a bit of context, this is, of course, I mean, I didn't come up with this. This strategy was mainly developed by Michael Plum, or I mean, over like the last 3 decades or so. And he actually already gave a talk in this seminar when he presented this technique maybe in a rather general setting, trying to showcase how wide the range of applicability was. Today, I want to do something different, which is I'm only going to focus on this specific problem. And therefore, hopefully I can go a little bit more into the details and help you understand precisely what are the different steps that you need to do in practice to use this technique. Okay, so the starting point, I mean, this should not be a surprise to anyone, since we have a Hilbert space, this norm, we can rewrite it using the scalar product. And so then we get this term on the other side using the adjoint. And so this norm is now just the scalar product of this operator times u lambda, scalar product of u lambda. And so this operator self-adjoint, we are in a compact domain, so it has compact resolvent. I mean, there's only discrete spectrum. And really, so we have immediately a lower bound for this, which is just the smallest eigenvalue of this self-adjoint operator times the norm of u lambda. So this is okay, not quite what we want, because here we have the y norm. So y is just L2 times c. So here we have an L2 norm. And what we need really is the norm is x, so x is h2 times c. So this is not exactly what we need, but once you have that, there are some a priori estimates which are actually quite easy to get in this case, sorry, which allow you to lift this L2 estimate into an H2 estimate in a sense. So this is really the most difficult part. And so no, this is a quite general question actually. So okay, I have a self-adjoint operator on a bounded domain which behaves nicely. How can I get rigorously a lower bound for the smallest eigenvalue? Okay, so that's the thing we need to do. And so that's what I'm going to explain. And actually, I'm not exactly going to explain it to you on this operator, but on a simpler one. So the operator I'm going to focus on, which is called this delta tilde, is just the second order part in L. So of course, you need to do more to solve this problem. I will touch briefly on that at the end. But to make the explanation simpler, yes, I will focus on this example. But the strategy is really the same. Okay, so main task now, get a rigorous lower bound for this operator. So so this is the operator, I will call this is the domain and the boundary condition. So just to fix the notation, let's call lambda1, order them in ascending order, the eigenvalues of minus delta tilde. And as I said, what we really care about is lower bounds, but okay, lower bounds are a bit tricky to get. And what's easier to start with are upper bounds. And so those upper bounds, they will actually help us to get the lower bounds. So let me tell you first about upper bounds. So again, let's start with easy things. This is stuff all of you probably know, but maybe you never thought before that this could be used to actually get rigorous bounds. So if I take any element in the domain of my operator, so in that case, it's just H2 with the boundary conditions, and I compute just minus delta tilde u, scalar product with u, then since this is my smaller eigenvalue, this self-adjoint operator, I know that this is larger than the lambda1 times u times u, okay? And this, of course, directly, as soon as this is non-zero, so as soon as u is non-zero, this gives me an upper bound for my smallest eigenvalue, right? I can just compute this quotient, and that's it. So this, of course, is very elementary, but the nice thing about this is that first I can make this very sharp, because instead of taking any u, I can just take for u a numerical eigenvector, which is, if I compute it very accurately, then this quotient would be very close to actually being equal to lambda. And also I can easily make this rigorous just by, I don't need to rigorously compute the eigenvector. I just take a good numerical eigenvector and then evaluate this rigorously using interval arithmetic. And then I get a rigorous upper bound, right? So the message is that upper bounds are it's very easy to get sharp upper bounds and rigorous upper bounds. And so that's for the smallest eigenvalue, but actually you can easily also do that with several eigenvalues at the same time. So to do that, you just have to generalize a little bit. And so instead of taking just one u in the domain, you take a family of them. The only requirement is that they are independent. And then this number here, you replace it with a matrix with all the entries being the different eigenvectors. Same thing here, this number, replace it by this matrix with all the ui scalar uj. So then you have to make sense of, okay, before I had this division between two numbers, now it's between two matrices, and the way to generalize that is to look at the generalized eigenvalue problem between these two matrices. And what you can show is that if you take the generalized eigenvalue of this between these two matrices, A1 and A0, then they give you upper bound for the eigenvectors. So this is really just a generalization of the one eigenvalue case. And really, again, this you can do easily in a rigorous way. And in a sharp way, if you take the U1, UN approximate eigenvectors. The only extra step is to rigorously solve this generalized eigenvalue problem. But in this case, A0 and A1, they are no longer infinite. They no longer are on Banach spaces or whatnot. They are just n by n matrices. Right? So if n is not too large, this is something you can easily solve rigorously. Okay, so now let's turn.
You still did not. You did not say which discretization you were using, or at this point everything is kind of general and this is.
Yes, like... it is. It doesn't matter at the moment. Of course, if you want very, I mean, there are some. The numerics play a role. I will come back to that later. But at this stage, I mean, it doesn't matter.
Okay.
It doesn't matter. You could whatever. This condition is, you have to be a bit careful with that, but I will come back to that later. Okay, so now we turn our attention to the lower bounds. And so first I'm going to make an assumption, and then we will see in practice how to verify this assumption. So I'm going to assume that the first and the second eigenvalue, they are well separated, and that I know an explicit number rho between the two. So if I do that, now I will play a bit with the operator and the spectrum and try to do something similar to what I did before. So first, let's shift the spectrum by rho, or equivalently, just look at minus tilde minus rho instead of just minus tilde. This way I have one eigenvalue, lambda 1 minus rho in the negative side and everything on the other side. Then I take the inverse, like this. Okay, so I just invert my eigenvalues. On the left side, I had only one, so nothing changes. And now I do the same thing. I take some v, I compute the scalar product, and since the spectrum is this way, I have a lower bound, which is 1 over lambda 1 minus rho. And now just, so this is positive, this whole thing is negative because lambda 1 is less than rho. And so provided this one is also negative, I can just invert this inequality. And now I get an upper bound, a lower bound, sorry, for the lambda 1, which is just this rho plus this quotient, just inverting this inequality. So this, it's almost something we like, not quite, because there is still this inverse here. And so to rigorously compute this, we would have to rigorously invert this, which maybe we don't want to do. Maybe it's not too difficult, but actually we can avoid it. And we can avoid it by taking not any v, but by taking v something which is minus delta tilde minus rho times something, so that the inverse, they cancel out here. All right, so if I take not any v, but v like this, and I plug it in, then the inverse now disappeared. And I only have the operator minus delta tilde itself that I have to apply, which is maybe a bit easier. And so again, this is purely computable, can easily make it rigorous with interval arithmetic, and can easily make it very sharp by taking you a good approximation of the eigenvector. So sometimes this is, if you write it a bit differently, this is nothing but what is called the temple quotient, right? This is, maybe this formulation is closer to the Lehmann method, but it's really the same in the end. Okay, and similarly to the upper bound, you can, so this is for one, the first eigenvalue, and you can do that for several eigenvalues at the same time. You just have to assume now, if you want upper bound for n eigenvalues, that the nth eigenvalue is well separated for the n plus 1 with a rho in between. And then you do the same again. You replace this number by the matrices with all the approximate eigenvectors. Same thing here. You solve the generalized eigenvalue problem, and you get lower bounds. Right. And so all of this, it's in fact as simple as the upper bound, except for this rho that you have, and you need to be able to do that, which is of course a priori you cannot, because that's exactly what you want, in a way. And so the way to deal with this problem and to find the rho, at least one way, is to use a comparison problem. So here is the situation for the moment. So this lambda 1, lambda n, those are numerical eigenvalues. I can compute them accurately, but I have no proof about them. The thing I have proofs about are the upper bound, lambda 1 bar to lambda n bar. And so now, if I know that there is a rho between lambda n and lambda n plus 1, I can get the lower bound, the way I just explained. But of course, at the moment, I cannot prove that the rho I chose is really, I need, of course, if I take it larger than this upper bound, I know it's larger than lambda n, but I don't know yet that it's lower than lambda n plus 1. So at the moment, I cannot do this. And so in order to do this, we're going to introduce this comparison problem and introduce this operator that is called delta tilde 0, which is almost the same as the original one, except that now instead of this coefficient which was depending on R, we take a constant coefficient here. And this we choose not in a random way, but we choose R max, so that just by doing an integration by part, you easily see that you have a comparison between the two. For the quadratic form, for any u, you have that this is larger than this. And this gives you comparison between the eigenvalues. It tells you that when you order them the same way, any eigenvalues for delta tilde is larger than the corresponding eigenvalues for delta tilde 0. Right? But note, the good thing is that this is just a Laplacian basically on a rectangle with reasonable boundary condition. So for this, of course, I can compute the spectrum by hand. I have explicit formulas for them. So I have this, which are in fact lower bounds for the eigenvalues, not very sharp, but rigorous lower bounds, and I can compute this explicitly. Right. So this is the picture. I know those are really rigorous. So let's assume for a second that I'm a bit lucky. I mean, of course, in practice, this is not going to be the case, but just for the sake of the explanation, assume the eigenvalues, they are really like this. So lambda 1, 0 is a bit smaller than lambda 1, a bit to the left, as it should be, but not by much. Same for lambda 2, same for lambda n plus 1 here. Then I can say, okay, this lambda 1 plus 1, 0, it's here. And I know by the comparison principle that this is a lower bound for the nth plus 1 eigenvalues of minus delta tilde. Oops. So I know that lambda n plus 1 is to the right of this. And so this, if those two things, the lambda n upper bound and the lambda n plus 1 lower bound, they are in this order, and there is some space in between, then any row in there, I have a proof that it's between lambda n and lambda n plus 1. So then I can really use the Lehmann technique to get also the lower bounds, right? But obviously in practice, you're not going to be that lucky. And so what's going to happen instead is that the eigenvalues, they are probably way more different. Like the lambda 2 is much further to the left and so on. And so in this case, okay, this is still a lower bound, but since it's here somewhere, I cannot use it to choose a row, right? I need to choose the row to the right of the upper bound. And this doesn't tell me that I can choose it here. Okay. So this is the last problem we have to solve. And for this, we're going to use what Michael calls the homotopy method. So, I mean, I know this is a bit technical, but this is the last technical slide. So try to hang on if you can, and then I will go easy on you for the last 5 minutes. So, right, so this is the situation, and we cannot really get the information we want directly. So we're going to go at it in the reverse order in a sense. And so we start with what we know. Let's say we have the force per eigenvalue here. And we are going to continuously go between this and the operator we want, introducing this delta tilde as this homotopy. And so if the only thing I know is that when S increases, the eigenvalues, they all increase. They all go to the right. This is because of the comparison between delta tilde 0 and delta tilde. So what I'm going to do is choose some intermediate step, S1, and let me explain you how to choose it. As I told you, all the eigenvalues, they must increase. And so I'm going to increase them little by little until for the third eigenvalue, the upper bound almost reaches the lower bound for the fourth eigenvalue. So the fourth eigenvalue, I no longer know when it is, I no longer care. I only know that by monotonicity, it must be larger than where it started. So it's somewhere there. And so if this is the picture, then somewhere in between here, I can stick a row and I can get the lower bounds. All right. So now if I keep going, this will cross. So the lambda 3, I no longer have information on it. So I'm going to drop it, but I'm only keeping this value for lambda 3 at the lower bound for the following, right? Again, I'm still increasing S. So the eigenvalue, even though I don't know exactly where it is, it must increase. So the lower bound is still a lower bound. And now I increase it again, same game, until the upper bound here almost reaches that. Then I stick a row, I get the lower bound, and I keep going. And hopefully, if I started with enough eigenvalues at the beginning, then at the end, the upper bound for my smallest eigenvalues is smaller than this lower bound. And I can do once again the same trick. And I get the rigorous lower bound for the smallest eigenvalue. So of course, on this picture, I had to make this interval quite large so that you could see something. But in practice, those intervals are very small. So this interval is really going to be super sharp, or at least reasonably sharp. Okay, so let's zoom out a little bit. Why did I try to explain to you all of this? Because we needed, as I explained to you in the beginning, technique to rigorously get a rigorous lower bound on the smallest eigenvalues of this thing. So okay, I explained it to you on a different problem, but we can use exactly the same strategy. The only thing that is missing is this comparison between something for which you can compute a spectrum. So I'm not going to write through all the computation, but it's not very complicated here. So you could do different things actually, but here what we did is find a comparison problem. So something for which all the eigenvalues are smaller than this operator, and for which the spectrum is expressed in terms of this delta tilde. So we don't exactly know it explicitly, but the eigenvalues of delta tilde, we can compute them rigorously, just as I described. So this is good enough to start the homotopy. So maybe I can give you some numbers just to give you a feeling of what's happening. So we start with a bit more than 400 eigenvalues of this delta tilde 0. For this, we have analytical formulas. And then we use the homotopy method between this and delta tilde. And at the end of the homotopy, we retain a bit less than 300 eigenvalues for which we have rigorous enclosure. And so if I have rigorous enclosure of those, have rigorous enclosure of the base problem for this operator, and then I can do a second homotopy between this base problem and the operator I really care about. And so we do that. This number of eigenvalues was chosen well so that at the end, there are only a few eigenvalues remaining. We don't want to do too much extra work for nothing. And in particular, we get a rigorous bound, which is okay. There is a number. Actually, the value of the number is not so important, but it's important that we have a number. It's rigorous and strictly positive. Okay. So of course, I had to choose some parameters there. So this is the size of the domain in the radial direction. So the alpha, as Maxi said, in this case is this is what describes on which side of the Hopf you are. The A just tells you where the limit cycle is, and the shear B in this case was taken just large enough for the Lyapunov exponent in the end to be positive. Maybe just one comment here. I mean, this will not be a surprise for the rigorous computing people, but as usual, those techniques down. So you have the purely analytic technique, you have the rigorous computing technique, and they actually complement each other quite well. So the reason I'm saying that is that typically when you have really in stochastic analysis, the place where you can usually hope for theoretical result is when the noise goes to 0. Because then you can do some asymptotics sometimes. I mean, it's not easy, but you have theory, large deviation and everything, which sometimes allow you to tell something when the noise is close to 0, right? For us, on the other hand, having the noise close to 0 means sigma being close to 0, so this is bad for us. But for us, when the noise is larger, everything is easier. And so in that sense, I mean, it's interesting and it's also, yeah. So I like it actually, that this is the easiest regime for us and not the other. Okay, so let's zoom out some more. Now we have the smallest eigenvalue. And the reason we cared about that is because we needed this kappa to use the Newton counter-wave theorem. So again, here are some numbers for this problem. So for the L operator, this is the epsilon. So I will tell you in one slide, Jean-Philippe, I guess this answers the question about what types of numerics I used. The kappa is okay, some number, and the gamma in this case is just 1, right? Because the only nonlinear term here is the product lambda u. And so when you look at this, the constant is just 1 here. So I get a rigorous enclosure of order 10 to the minus 11 or something in this X norm, which is so H2 norm. Right. So here are some pictures. So on the left is the eigenvalue, the eigenvector eta for L. On the right is the phi for L star. And so of course, this is not the true solution. This is the numerical, the approximate solution. But what I've just proven is that the true eigenvector is in a small neighborhood of size 10 to the minus 11 in H2 norm, close to that. And for the other one, I don't show you the number, but you can do something similar. Okay. So, okay, maybe a few words about the numerics now. So, of course, you could do, you don't have to do things unique way at this stage. You could do different things. For us, I mean, of course, I'm a bit biased here because I'm what Michael would call a Fourier guy. I do a lot of numerics using spectral analysis, so for me it was quite natural to do that. But it also turns out to be quite efficient for this problem. So what we do is, for the discretization, we use Fourier-Chebyshev series. So Fourier in the psi variable, for which we have a periodic boundary condition, and Chebyshev in the R variable, for which we have Dirichlet boundary condition. And so one advantage of this, besides being very accurate, is that, as I mentioned before, when you do the estimation for the eigenvector, the rigorous upper bound and lower bound, one requirement is that the approximate things you take, they have to be in the domain, right? And so in this case, in the domain, being in the domain means having some smoothness. So for delta tilde, it's H2. Actually, when you look at the FF star thing, it's H4, and also satisfying some boundary condition. So in this case, the smoothness is for free. Just those things that are smooth as you want, are analytic. And actually, the boundary condition in Fourier is also for free. And you just have to worry about the boundary condition in R, the Dirichlet boundary condition, and this turns out to be quite easy to do numerically and rigorously.
Sorry, I mean, this R minus R minimum shouldn't be 0. I don't know. So
in our case, it's this.
Yeah, but for the original problem, in a sense, I know.
For the full problem, exactly, you would need this to be 0 and this to be plus infinity.
Yes.
But that's what we, as Maxi said.
Okay, so this is conditional Lyapunov.
Exactly. So we are only looking, I would be very interested, and maybe it's doable to do something for the non-conditioned Lyapunov exponent, but we didn't do that yet.
Oh.
So we really only looked at the conditioned Lyapunov exponent for the moment.
And where this constant B enters into your L operator, it enters into F or G, or I don't know. This B,
which
shear constant.
Yes.
Right?
So okay, let me go back. So the B, it comes in the
okay.
In here.
Okay.
In here.
Okay. Okay. Mm-hmm.
Yeah. That's why, I mean, you only see it in the finite dimensional part, which is why I didn't talk about it, because all the estimates I explained there for the proof for controlling the tail and everything, and it's really in the finite dimensional part where you do the numerics that it plays a role.
Uh-huh.
Okay, so yeah, so as I said, this makes it easy to check that we are in the domain. But of course, here I should mention, I mean, I don't know if Michael is here or not, but if he would make the comment, I think, and he would be right to do so, is that you don't have actually to exactly be in the domain. There are techniques which I think the theoretical part goes back to the late 80s.
I will make this remark.
Okay, yeah, but you're right to do so. That there is this Gurish trick, which is actually a very, very nice argument, which allow you to go around that if you need to. And so actually you don't have to, you have to work a little bit extra on the numerical side and on the theoretical side. And here, okay, let me just say that I was happy that we didn't have to do that, but if we needed to, we could have done that. It's just that by using the spectral techniques here, we don't even have to worry about that. But if you're thinking about a similar problem, or you think, oh yeah, but I would like to do this, but imposing the boundary condition is difficult, then there are ways around that.
And I also assume that the spectral approach gives you very good effect,
look at
right?
Michael's talk or at the reference on the webpage. Yeah, also, but the defect actually here, we don't care so much, right? Because if you look, this is what? Order 10 to the -4 or something. So we really don't need that small of a defect to get the contraction. It's just, okay, we have a smaller defect, it's nice, but for the proof, it doesn't matter so much. Okay, and so again, there is no unique way of doing this. As for since we use MATLAB, we are very happy to use INCLAB for the interpolate arithmetic computation. So in particular, those eigenvalue, finite size, general eigenvalue problem, INCLAB does that for you. You don't have to do anything, so that's great. But okay, and so the last slide now. So the rigorous computation of this Lyapunov exponent, so it's given by this formula. The E is just given, Maxi explained it a bit to you where it came from. And so now I explain how to rigorously validate an eigenpair of L or L star, but we need to check that we have the correct one. And so what I mean by the correct one is that one characterization of those E times phi is that they are the eigenvector associated to the eigenvalue with the largest real part. So this, okay, is clear, but this is hard to verify in practice. I mean, again, you could think about doing it, but then you need to do excluding, and I mean, this takes some extra work. So luckily for us, there was another characterization of this eigenvector that we could use, namely, at least for eta, is that eta is the unique, so unique up to normalization, eigenvector that is actually positive inside the domain. Right? So this comes from probability, some probability paper, they tell us that. And okay, so maybe it's easier if I explain it while looking at the picture. So this is eta. And now if I can prove rigorously that eta is strictly positive, then I know it's the good one. And so I have enclosure in H2, we are in dimension 2, so I have enclosure in L infinity by Sobolev embedding. So if I go just a little bit away from the boundary, I can easily show that this number, which is positive on this picture, is actually also positive for the true solution, right? So everywhere it's fine, except at the boundary, because of course I have 0 boundary condition. So very close to the boundary, I cannot do that anymore. The solution will get arbitrarily close to 0. Okay, that's not the end of the world, because so again, you could do something more sophisticated, but here what we use is that this eigenvector actually it's one-dimensional. As you can maybe guess by this picture, it doesn't depend on psi. And this is something you could already guess by just looking at the operator L. It's not the case for L star, but it's really the case for L. It's because this F term, it only depends on R and not on theta, of psi, sorry. And so since this is one-dimensional, now the H2 in 1D embeds in C1, and so actually I have C1 enclosure for this. So I can compute the derivative at the boundary for the numerical solution. I check that it's strictly positive here and strictly negative there. And then, okay, I get some small error bounds, which allow me to say that close to the boundary, the solution might stay positive. And then I glue it with the rest. Okay, so this is how we validate that, oops, wrong way. We validate that eta is the good eigenvector. And so in particular, that it's in fact associated to the eigenvalues with the largest real parts. And then for the phi, I only have to check that they are associated to the same eigenvalue. And for instance, I just compute the scalar product. If the scalar product of these two is non-zero, then they must be associated with the same eigenvalue, and that's it. And so finally, I can rigorously compute this integral. I get a number. It's positive. I'm very happy. I mean, of course, I choose the parameter so that this was positive, and that's it. So thank you for your attention.
Very nice, very nice. Thank you. Thanks to both our speakers today. We can now open up the floor to questions, other questions and comments.
Can you show previous slide?
Sure. Which one?
Yes, yeah. So you had your, so you have your alpha positive right here. Was for the,
yes, alpha is equal to 1 here.
Yeah, so.
And we,
yeah.
But still, I mean, this E, it's somewhere positive, somewhere negative.
Yeah.
And so.
So you don't have for this lower row on the first slide, right? I mean, when the.
No. We would probably be able to get the same thing, but we would need to take B much larger. And probably numerically it's harder. We didn't try it, but in theory it would work, but in practice I'm not sure, I must say. We didn't try that yet.
Okay, so the dynamically be bigger helps, but numerically it's kind of gets harder, right?
Yes, exactly.
And how big were the computations in terms of time or something?
So this, I mean, took 2 or 3 hours on my laptop. But actually, so the main part of the computation is computing non-rigorously this the eigenvectors for the homotopy method. So there maybe Michael has a comment because I'm not an expert on this. It's the first time I do that. So maybe I did not do that in a super optimal way. But here to find so here I only two intermediate steps, but in practice I have a couple of hundreds. And then I have to find if those threshold every time. And I don't want to be too lazy because if the threshold is too far away, then I lose a lot in the eigenvalues and I don't have enough eigenvalues at the end. But, and so here, I mean, actually the most time the algorithm spent is in non-rigorously computing these eigenvalues to find the S in a kind of dichotomy method. So I don't know, Michael, maybe you have a very smart way of doing that, and usually this is not where your code spends the most time. I don't know.
Yeah, I think that the non-rigorous part, I have no smart idea to improve that. So for the non-rigorous computation, that's the approximations. You really need to do the full computation. For the rigorous part, you can. It is sufficient to look at the highest eigenvalue at which you just are during your homotopy. Then you don't need to compute the rigorous bounds, the rigorous lower bounds for all of these eigenvalues. At the beginning of the homotopy, you have many of them, and you don't need to compute rigorously all of them, but only the highest ones, right? You can go along the upper line of the homotopy, so to say.
Sure.
But as you say, for the non-rigorous approximations, I have no idea to do it different from as you did it.
Yeah, and so probably I could make the code a bit faster, but since most of the time is spent there anyway, so this is, yeah. But as I said at the beginning, I mean, of course, this is not something I understood first, because otherwise maybe I would have done things a bit differently. But we're really not using a lot of the structure of the problem here, meaning we kind of ignore that we have a sort of Laplacian in polar coordinates and just look at this thing. And then, of course, maybe it would be better is to really think about this as go back to the Cartesian coordinate, take the Laplacian on this annulus plus some first order terms and work there. I don't know.
I have another question or another remark or mixture of question and remark. So
Sure.
you comment on the Görisch extension by saying that, okay, if we have smooth ansatz functions, basis functions, then we don't need a Görisch extension. Of course, that's correct in your example, but if you have this L star L problem, right? So there's also a question of smoothness of the coefficients, right? Because when you have this the L star operator is a differential operator, and for for being able to apply this operator L star L or F prime star F prime, so then there are also derivatives are acting on the coefficients of F prime. And
so you mean if the coefficient of my differential operator, so the F and the G here, they are not very smooth?
If they have non-smooth.
Okay. Yeah. Sure. Yes.
Then you can't help with that. So that's the given problem, and you can't change it by choosing smooth basis functions. But nevertheless, in this case, the Görisch extension still helps.
Yes,
because everything is formulated in the bilinear form domain and no longer in the operator domain. So I would say that's the main advantage or the main characterization of the Görisch extension is that you are always in the bilinear form domain, not in the operator domain. And but in your case, when F and G are smooth, then of course there's no difference.
Yeah. No, you're right. I mean, as I said, maybe, I mean, I looked at it actually because at first it looked like we were needing it because there's something maybe would be interested. So there is a small twist here, which is a bit interesting, is that the base problem for this thing and this operator itself, they don't have the same domain actually.
Yeah.
And so even if you stick with the operator form or the bilinear form, you still need a way to compare the spectrum of the two. And so we do that, at least theoretically, by going via the bilinear form. It's just that in practice, we don't use it, but to compare the spectrum, we actually go via the bilinear form. Because otherwise, I don't know how to easily compare the two of them.
In the Görisch formulation, that might be a bit easier.
Yes.
But maybe the numerical results will be not so much different. But actually, I have another question. So concerning going away from this ring to the full R2. Well, you know that the Rayleigh-Ritz method, which you applied for upper bounds, and also the Lehmann-Meili-Görisch method, also works on unbounded domains.
Yes.
That means in principle, one can apply the whole stuff on the full unbounded domain. But I agree that I also have no appropriate idea how to choose the base problem in this case. That's because then you have this factor 1 over r square in front of one of the coefficients, and that is if it's on the full space, you have no lower bound for that. You have no upper bound for that, and then it is difficult to compute a base problem. But the method altogether, in principle, can be applied on the unbounded domain.
Yeah. But the thing is, so these things, they look singular, but it's only because it's polar coordinates. I mean, if you go back to the Cartesian, the singularity.
Yes.
So I mean, I'm not sure. I was very happy that Maximilian, he was also doing this. He had this framework for the bounded domain, and to start, I think it was a good place to start. But definitely we'll be looking at the full space domain at some point. And I mean, I would be interesting to see if we can use basically the same idea, but maybe not in the same coordinate or something to do the whole space.
The problem would then be, just to comment on that briefly, if we go back to these Cartesian coordinates, we probably would have to work in 3 dimensions, right? Here we could reduce it to this radial and this angular coordinate, where the angle psi really incorporates the angle of the nonlinear and the linearized system. Whereas if we go back to the Cartesian, we probably have these 2 dimensions plus the dimension of the direction, like angular direction on the tangent space. So that would add probably a dimension, and I don't really see how to work around this. But yeah, so we.
But maybe there is actually another problem with this, with going to the full space. Namely, if you take something like the Laplacian as a base problem, then you don't have eigenvalues, right? You only have essential spectrum, right? Starting from 0. And the whole homotopy idea breaks down in such a case. So you need eigenvalues below the essential spectrum to start with. Otherwise, well, it's quite clear when you look at the homotopy picture that if you have only essential spectrum, then it doesn't work. So this yeah, okay, maybe that's enough on that. So that's actually. That would be another problem. So you would need, in case of working directly on the full space, you would need some very sophisticated space problem, not just Laplacian, but there must be Laplacian plus some perturbation which creates eigenvalues, which, however, nevertheless, you know in closed form, or at least you can compute enclosures too. Right? So it's a bit. I'm sure it's not so easy, but nevertheless, I would find it interesting to look at that.
We should definitely discuss that at some point.
Yes.
Yeah, maybe just one last remark on that, also in terms of where it comes from. I don't want to give the impression that this whole space problem is necessarily also the one that you want philosophically. I mean, part of this idea of the conditioned Lyapunov exponent, I mean, still, of course, this is like a completely interesting and fine problem to do. I'm just saying that we're doing this conditioned Lyapunov exponent problem on a bounded domain. We're forgetting trajectories which go beyond this domain, also for a certain physical reason, because we claim that if we come from the white noise model, we just say, okay, there's this potentially global white noise, but we are not even so interested always in exploring the whole state space with the noise. We are really interested in this huge proportion of trajectories, which mainly stays in there. So just, this is also, I think, as such, so this is not only an approximation to the full space problem, but I think as itself also a result we want. But this doesn't diminish the fact that it's super interesting also to do it for the whole space. Yeah.
I have one remark. Okay.
Yes.
Okay. You see. So since you see in your problem there appears a self-adjoint problem. So yes, homotopy method is very nice. It works well. But I suggest you see, because it is a bounded domain self-adjoint operator, you can apply FEM finite element method, and it's very straight. And I think in some sense it's very simple, straight, can easily obtain the lower bound for the eigenvalue for the operator. Yeah.
Yeah. So you're definitely right to make that comment. I should have mentioned that actually. I was planning on saying that this was not the only option, and I forgot that you also had developed technique for that. But you're completely right. I mean, so what happened actually is that I'm not so familiar with this eigenvalue problem, And so when we discussed with Maxime, then afterwards I met Michael in Montreal at the theorem actually. And then I was like, I should just ask him how he does it. And he explained his techniques to me. And that's why, but I'm not saying there are not no other alternatives that could definitely do it differently there. Exactly.
But then you definitely need the Görisch extension for finite elements. Otherwise, the elements have to be too smooth, right?
Yeah, sure.
Oh,
actually, go ahead.
By the way, for the eigenvector, if the problem about self-adjoint problem, so it's about the problem with it to give bound or eigenvector or some eigenspace. So there are some strict and very nice result, including my recent result and also the result from Kahan. Yes, so you can see some my preprint. So they are very beautiful results to give estimation for eigenvector or eigen subspace. Yes.
Okay, but you need self-adjointness for that, right?
Yes,
you need the problem to be self-adjoint, or not necessarily. Yes. Yeah, because in our case, as you see, because of the first order term, this L is not self-adjoint. So that's why. Different.
But it is self-adjoint case then. You see, okay.
So we could use it for the F star F problem.
Even for cluster values or nearly clustered, no problem.
Okay.
Okay.
I have an additional question. If there's nobody else, because
Sure, I think you can go ahead.
You said that you had no idea to apply this, what you called method 1, where you first compute an approximate inverse and then estimate the difference between the true inverse and the approximate inverse, and then get the upper bound also for the inverse, for the exact inverse. What is? Can you explain? You could, for example, think of taking a finite dimensional computational subspace and then project this operator into that space, and then compute the approximate inverse there, which is then just a matrix again, and then use that as the approximation you're looking for. Why does this not work?
But then, I mean, okay, if you think about it in spectral, you do the finite part and then you need a tail. And usually the tail are either the eigenvalue or the identity if you pre-multiply by inverse Laplacian, for instance. But this you know exactly usually, or very accurately. In our case, because of this non-constant term here, really in spectral, the tail would be ugly. There is no I cannot just say that the diagonal tail is going to approximate well this. This is not true. At least I don't know a basis. Maybe the Wernicke polynomial would work, but otherwise I don't know a basis in which this is true.
Okay, so it's actually a question of choosing a good basis.
Yeah. Yes.
Yes.
So in spectral, I mean, I don't. Of course, in the finite element I think it's more or less equivalent, but I understand it less. But I think it amounts to not understanding so well the inverse of that operator. And usually you just multiply by Laplacian -1, which on a bounded domain you can say a lot about, and here it's a bit more complicated.
Yes, because the leading terms have non-constant coefficients. That's the problem.
Yes.
Yes. If you think of the second derivative in psi, so in Fourier this is diagonal, but then you have this 4 over r squared and Chebyshev, and that's going to make things like off diagonal and tri-diagonal, and then you have the second derivative in Chebyshev, which now is a fully lowered triangular matrix. So that operator is in fact quite nasty.
Yeah, but that's So I wouldn't look at that in Fourier Chebyshev.
No,
definitely not. I mean, I thought about it at the beginning, and I quickly realized it was hard.
Yeah, it looks
well. In a sense, I'm happy about that, because that enforces you, in quotation marks, to use my own approach.
Exactly, that was a good opportunity for me to learn it. Right?
Yeah, but somehow finite elements, as Shufeng said, I mean, using some sort of finite elementish approach to that could still.
But still with the approximate inverse, you mean the Nakao, Yamamoto, Watanabe way?
Yeah.
Yeah, but then, okay. I think in the end we would have similar problem with the a priori estimates you need to, because they do the same, right? It's a finite dimensional thing.
Yeah.
And then on the tail, you assume that you can do everything by hand, basically. And I'm expecting, okay, maybe not, and I would be very interested in that the case, but I'm expecting there to be a similar difficulty in a sense in understanding the tail or getting explicit enough estimates. Or
maybe.
I mean, maybe
It's
yeah.
a tail. Well, in Akao's approach, it's the tail, so to say, is not in Fourier space, but the tail is in function space. This error, this projection error.
Yeah, you would need good, good estimation error. I mean, error estimates based on your finite elements.
Yeah, but not for the usual Laplacian, but for this thing.
For this strange thing, yeah.
Yeah.
If you apply FEM, I think at least it can save you much time because it's very strict, only one step. Okay.
I have an additional question, which is not, maybe it's not the computer-assisted part, but it's this sigma. You explained already, Maxime, when the sigma tends to 0, then you get in trouble because the leading coefficient of the leading operator has a small coefficient. So,
yes.
But I'm not sure. So there is so that seems to be a singular perturbation problem. Is that right? So that I have never seen computer-assisted proofs for singular perturbation problems, but there are. You see, in analysis, there are approaches to singularly perturbed problems, which give something for the limit. But my memory is too weak to remember details.
So in this context, sure I don't know. I don't know in this context, but that's what I said at the end. That maybe if you could hope to do something by hand somewhere, it was definitely in the sigma goes to 0 limit. Maybe there is, but. And it's kind of cool that for us it's hard there, but maybe there is some hope to do something theoretically. And on the other side, where by hand is harder, we can do stuff.
But in that context, so you see, what does really happen? You see that maybe that's a question to Maxime Engel. What happens if that sigma is small? You see, you showed us this stochastic attractor with this strange curve, which appears for sigma equals 1. But if you then diminish sigma, what happens? Does this curve disappear as an attractor suddenly, or does it contract to something, or what happens?
So if you let sigma go to, I mean, if you take the limit, it really depends on its interplay with the other parameters. I think this really depends on the scaling regime, also with the shear and potentially also with the alpha. So there are definitely small noise results. So when the sigma goes to 0, where you can always show that there's the synchronization. So there's the contraction to the point. Of course, at sigma equals 0, it really only depends on alpha, but in the limit, sigma going to 0, you can have both. You can have synchronization or you can have the chaotic attractor, but this really depends on the interplay with the other parameters and the appropriate scaling of the others. But as such, if you fix the shear, and let's say you fix an alpha, I think it probably doesn't even matter. Let's say a small alpha around 0, either negative, positive, and you fix the shear and you let the sigma go to 0, then usually you would see a synchronization. So then you wouldn't see this chaotic movement.
And that's a continuous process. So there's no sudden jump in that process, but it continuously contracts, so to say.
Yeah, but then of course there is the sudden jump at sigma equals 0 in any case, if you have, for example, the alpha bigger 0, because then you would have contraction to a limit cycle. And this limit cycle collapses for any sigma bigger 0. So and also in the limit sigma going to 0. And then there's a sudden jump at sigma equals 0 where this collapse doesn't happen. And you actually have a, very different behavior because you have this limit cycle. And this limit cycle can't be sustained for any kind of noise. This only happens really when there's no noise.
In a sense, that shows that this is the computer-assisted approach for very small sigma is really difficult because they have the strong dependency on the other parameters. And you see, in a computer-assisted proof, you always automatically compute also the same proof for neighboring problems, and that shows that this is really difficult. I understand.
I guess it's 11:40 here, so it's 5:40 already in Europe and very late in Asia. So I would say that we'll probably pause and stop the questions for now. And we should all be very thankful to Maximilian and to Maxime for great talk. Lots of material, very exciting. Thanks a lot to you both. All right.
Yeah, thanks a lot for sticking around. Sorry for having a slight of lengthy introduction, but it seemed that people took something from it. So yeah, thanks a lot.
Absolutely.
Very nice. Thank you both.
Thank you very much. Bye-bye, guys.
Bye, yes.
Bye-bye.